On the second part of page 10, we're going to learn a second way to solve logs. So the way we learned at the beginning, where you move all logs to the left, and then write as a single log, and then loop and swoop, that works for every log problem. This only works for problems that have logs on both sides. So for instance, this problem does not have a log on both sides, so I wouldn't be able to use this new way. This one, you'd have to move the log over, then you could use this new way. And let's see, this one would not have worked because see how we have a number over there? So it has to have log on one side, log on the other. It can't have a number. So this new way wouldn't have worked with this, but it would have worked with this one. So we could have made one log on the left, kept that log on the right, and use this method. So it's a picky method. You have to have logs on both sides, and there can't be numbers like hanging around. So this is equivalence of log expressions, and we have the same expression in exponentials. So we're going to learn that if in the next section, if we have 3 to the 2 equals 3 to the x plus 5, let's say, if the bases are the same of exponents, you can solve them by equating the arguments. And that's called the equivalence of exponents property, just like this is the equivalence of log property. So if the bases are the same, solve by equating the exponents. Well, since exponents and logs are inverses, they share some of the same properties. So this one says if the bases are the same, and you have one log on the left and one log on the right, you can solve by equating the arguments. So here we equated the exponents when the bases are the same. With logs, we equate the arguments when the bases are the same, and that's how we solve. So if we had log of x equals log of 2x plus 3, let's say. We go, oh, these are both base 10. We have one log on the left, one log on the right. So we would solve by equating the arguments. So if the bases are the same in exponentials, equate the exponents. If the bases are the same in logs and you have one log on the left, one on the right, equate your arguments. Bases are the same, equate your arguments. Then of course you go ahead and solve, subtract 2x, subtract 2x, and so on. So notice all three of these next examples have logs on both sides, so they all fit the pattern. But the key is you have to remember there can only be one log on the left and one log on the right. So you still have to use those properties that we wrote down at the top of page 9. Subtraction turns into a single log of division. Addition turns into a single log of multiplication. So you still have to do those because I can't have two logs on one side ever. I have to combine it to a single, have to combine this to a single. The only one that's ready to go is this one where it's already a single log equals a single log. Okay, so write as a single log first. So since that's subtraction, we learned that subtraction goes into a single log of division. So the positive log, its argument goes in the numerator. The negative log, its argument goes in the denominator. And then I have log of 3. Okay, so all I did was take those two logs and write them as a single log using our properties from section 8.6. So now that we have log and log, notice they're both base 10. Now we can do this. If the bases are the same, equate the arguments. If the bases are the same, equate the argument. So we get 5 plus x over x minus 5 equals, the argument here is 3. Since the left side's a fraction, remember you want both sides to be a fraction so you can easily set your cross products equal. So we have 3 times x minus 5 equals 1 times x plus 5. So this is going to be 3x minus 15 equals 1x plus 5. And then we just simply solve for x. So all x is on the left, so subtract 1x, subtract 1x. 2x minus 15 equals 5. So add 15 over. We get 2x equals 20. So x equals 10. But remember, this is a log problem. Every log problem has to be checked. So go up to the arguments and plug 10 in. 5 plus 10, is that a positive number? Yes, it's 15. 10 minus 5, is that a positive number? Yes, it's 5. So then I can say, yay! My solution is 10, and you need to put your valid solutions in solution brackets. That's how you show your reader it's valid and it's not extraneous. So that is called the one-to-one log property, or the equivalence of log property. So you make one log on the left, one log on the right. As long as the bases are the same, you set the arguments equal. And then just solve from there, and because it's a log, it does have to be checked. Okay, so on this next one, do you know what? Good time to shut off the video. I would shut off the video and try this because this is a special case, so it won't be a good one to practice on your own. So I would try this one on your own. So shut the video off for a minute, work it, and see if you can get it. So our goal is to get one log on the left, one log on the right. Well, I already have one log on the left. So now I have to use my properties. Addition goes backwards into a single log of multiplication. So everybody remember that from the last page? So addition goes backwards into a single log of multiplication. So that's from the last section. Now you guys know why I harp on you. Don't miss homework, because it comes back to bite you. Well, this is one of those. If you didn't do the properties homework, then you're going to be lost on this section because you're not going to know how to go to this step each time we do it. So addition turns into a single log of multiplication. So now we have the one-to-one log property. We have two logs. They have the same base, which is e. So we're going to solve by equating our arguments. So 3x equals 4. I'm going to go ahead and distribute just to save a step. 4x minus 12. Solve for x. Minus 4x minus 4x. And we get negative 1x equals negative 12. So divide both sides by negative 1. And we get x equals 12. So now we have to go into the original and make sure it makes all my arguments positive. So put 12 in. 3 times 12 is 36. That's a positive number. This doesn't have an x, so I don't need to plug it in. This one does. 12 minus 3 is 9. Yep, that's a positive number. So now I can go, yay! My solution is 12. Because it made this argument positive, it made it 36, and it made this one positive because it made it 9. And this last one is one of our special cases. You don't probably know that just by looking at it, but I can see when we equate our arguments, the x's are going to cancel. So I know whenever x's cancel, you learned in previous classes, that means it's either all real numbers or no solution. So step 1 is make one log on the left, one log on the right. Done. Step 2 is if they both have the same base, we are allowed to set our arguments equal. So the first argument is 6x plus 2. The second argument is 6x plus 7. So again, that's called the one-to-one log property or the equivalence of logarithms. So if the bases are the same and you have one log on each side, you can equate the arguments. I do want you to know that if there was like a 2 out there, you can't use this method. Okay? Because when you're doing your homework, you're going to have to know which method is. So on this one, you'll have to use the first method where you bring the log over to the other side and do loop and swoop. So if there's a number out there, then you can't use this method. It can just have one log on the left, one on the right. Okay, continuing on solving, when we subtract 6x from both sides, we go, oh, wait a minute, my x cancels on both sides. So whenever that happens, you should have learned in previous classes that you bring down the next line and you look at it and say, is it true or is it false? Well, this is a false statement. False statements mean no solution. So you can write no solution like this, or you can write it like this, or you can write it like this. Don't use a combination. It's one of those three. So take your pick, and I'm sure Alex is probably picky about which one it wants. So, but when you're doing a paper pencil test, they all mean no solution. And again, if this had been 7 equals 7 is true, then the answer would have been all real numbers. But because it's a false statement, it's no solution. Okay, that's all for 8.7a.